So in this video, we're going to take a closer look at myoglobin. And myoglobin's purpose is to carry oxygen to muscles. And so oxygen, or myoglobin, we can study its structure and its uniqueness and what makes it myoglobin. But we need to understand that myoglobin needs to bind oxygen at a certain point, and that at a second point in its existence, it needs to release it. And so we need to just use some mathematics to describe the binding and release of oxygen to myoglobin. And so this process of it binding oxygen and releasing oxygen is a reversible process. And so we can have an equation that represents this in a general way. So this reversible binding can be described like this. We have P standing for the protein, or in this case myoglobin, plus the ligand. Okay? And the ligand is what is binding to the protein of interest. And in our particular example, the ligand would be oxygen binding to myoglobin. But we're writing this in general terms, so we can talk about other proteins other than just myoglobin. And that's going to be an equilibrium process where you have the protein that is bound to the ligand. So what we have here is we have unbound on this side and then bound on this side. Or the way the text actually uses it, says it, we have unoccupied and occupied. That's another way of referring to it. Okay? Now we have this equation right here. We have something called Ka, capital K, and that would be equal to the concentration of the occupied state divided by the unoccupied state. We might need another marker. Okay? And that is equal to the lowercase ka divided by lowercase kd. Now these right here, let's describe what this equation is. Right? So we understand how we got the terms the way they did here because this is an equilibrium process shown right here. Right? Products divided by reactants. We've seen that many times. Now, this Ka is called the association constant. Okay, that's the association constant, which is measuring how well does this ligand associate with the protein. And the association constant has units. Ka equals inverse molar. Right? And so what that means is if this value is a large number, then that means that the ligand binds very, very well to the protein of interest. But on the flip side, if we have a small Ka, then the ligand doesn't want to bind with the protein very well. Now, we have to take a little side note here. Okay? This Ka, you've seen it before. And in organic chemistry and general chemistry, you called that the acid dissociation constant. Okay. Now the way it's been drawn, Ka, Ka, you would think that they're the same thing, but they're not. This Ka in relationship to the equilibrium process of proteins and ligands is the Ka, the association constant. But when we talk about acids and bases and things like that, the Ka is the acid dissociation constant, which tells us how easily does the proton get ripped off of the molecule. So they look the same, but they mean different things. So context is very, very important when you're trying to figure out, oh, there's this Ka, what does it mean? Is it an acid or is it talking about protein equilibrium? Okay. These right here, those are the rate constants. Okay. So that's the rate of association, so going in this direction. And Kd is the rate of dissociation, PL breaking apart into P plus L. So these are all rate constants, okay, so dealing with kinetics and whatnot. And we will talk more about these Ka, lowercase ka and lowercase kd later. Okay, that will be in chapter 6 if I'm not mistaken. Okay. So now that we have this equation here, what we're going to focus our attention on is just this part right here. Okay? And we're going to do some rearrangement here. I'm going to take and rearrange this in such a way as to multiply both sides by L. When I multiply both sides by L, we're going to get something that looks like this. And P, like that. All right? So from this, we can see mathematically that the ratio of bound to unbound, or occupied to unoccupied, that ratio is proportional to the amount of ligand that you have present. So as the concentration of the ligand goes up, then we're going to get more of the protein and the ligand bound to one another. The ratio will go up. And that makes sense mathematically. But when we take a look at this process within cells, and when we focus on proteins that undergo this equilibrium, more often than not, the ligand concentration is so high. And it's because it's so high, this concentration of the ligand is relatively unchanged as this process when that process occurs. So let me illustrate what that means. Okay, so let's erase a little bit of this. Let's just say, I'm just using numbers here just to illustrate a point, okay? Let's say we have the ligand. And let's say we have 20,000 of them. 20,000 ligands in the cell, okay? And just to make this example drastic, let's say we have 2 proteins, and the X's right there represent the binding site. So the ligand is going to bind where that X is, okay? And so our protein concentration is 2. We have 2 of them, but we have 20,000 ligands in our example. So when that ligand binds to the 2 proteins, what do we have? We'll have our protein with the ligand and another protein with the ligand. And then what would our concentration be now of the ligand if 2 react or bind to the protein? We're going to have 19,998, all right? So what I'm trying to get at is that within the cell, the ligand concentration is drastically higher. And so this relationship that I just talked about, that it's proportional to the concentration of the ligand, kind of falls apart because, look, we go from 20,000 to 19,998. The concentration is relatively constant. Right? It doesn't change. So we have to look at this binding here in terms of a fraction. Okay? There's a better way of looking at it. And the better way of looking at it is when we look at it in this way. We're going to use this term y, okay? And that is just going to be a variable that describes the fraction of the binding sites within the protein. Binding sites, oh, I missed it. We're going to need some more space. So I'm going to erase this board. Try to write a little smaller here. We have binding sites that are occupied. Divided by the total binding sites. So when you have your protein in a cell and you have all these ligands floating around, just because you have enough ligand to go into every single binding site, it doesn't necessarily mean that will be the case. So what we want to do is look at this ratio of how many sites have the ligand bound to the site divided by how many total sites there are. Okay? And so this y equation now, okay, space management here. So what we can say here is, I'll rewrite this equation, y equals the binding sites occupied divided by total binding sites. Okay, that can equal concentration of how many are bound. So you see binding sites occupied, that's what that represents, divided by the total. And how would we represent the total amount of binding sites? Well, how many sites have the ligand bound, plus how many sites that are not bound. And that would equal the total. Okay. Now, what we can do here is take the equation that we've seen already, the association constant, and we got it to this point. We said Ka times L is going to equal that ratio. We've seen that equation already. You can't, it's getting cut off a little bit, isn't it? So, let me pause this for 1 second. Okay, just had to adjust the camera. So we've seen this version right here. Now I'm going to make another adjustment. I'm going to multiply both sides by p. And when I do that, we can make the equation now look like this. And that's going to equal this. Okay? Now, look at what we can do. PL equals all of this. So we can take this term right there and substitute it in for that, and substitute it in for that. Okay? And so when we do that, this equation now is going to look like, we have Ka times L times our P. That's our PL. And then we have PL, so we write the whole thing all over again in the denominator. Plus P, like that. Okay, so Y equals this, equals that. Now it looks like that. And at the end of the day, you can take this version right here and you can simplify it down. Remember that in algebra class where you have to simplify an equation? Well, that's what we're going to do, but I'm not going to spend time in this video going through that math, but it might be good for you to do that. But I'm just going to give you the answer straight up, okay? So Y can be represented by looking at in terms of the concentration of the ligand, okay, plus 1 over Ka. So when you take this and simplify it, it's going to turn into this right here. Okay, and this is a very valuable equation because when you have a ligand and you have your protein, you want to find your Ka. And the way that we can do that is if we do a plot here. And on the y-axis, we're going to have 0, 0.5, and 1. And the y-axis is that variable right there. So let's, all right. And then on the x-axis, the x-axis, we are going to have and track as you increase the concentration of the ligand. So these can be arbitrary units, like I'm not too worried about what those units are at this point. And what's going to happen is you're going to track the y value with respect to the concentration of your ligand. So you're going to get something that looks like, well, a little bit. It's going to look more like this here. Drawing a curve today is not so easy. Something like that. And I drew it above 1. It shouldn't be, so let's extend out our y-axis here a little bit. And I'm drawing it off the board here, okay? So I need to, since you can't see that very well, looks like I'm going to have to redraw that. All right. Sorry about that. Let's just draw a smaller one, shall we? Okay. So that will be 1, that would be 0.5, and this is 0 in terms of the y-axis and then the ligand concentration. Okay. And so what we're going to have is a curve that looks something like this. And at this point, if we go from 0.5 all the way over, and then come down here, right there, that point on the x-axis right there, that is 1 over Ka. So what does this 0.5 mean? Okay. Well, that simply is y equals 0.5. Okay. So that means that at this ligand concentration, okay, at that concentration of ligand, half of the binding sites are occupied. And then the other half of the binding sites are unoccupied. That value right there is really, really important. So that 0.5 of y, that's the concentration at which half of the binding sites have been occupied with the ligand of interest. Okay? So that's how we would find our Ka, extrapolating down. And remember that Ka by itself is inverse molar. Now, the easier way to do these types of experiments is to look at the Kd. Okay? So what would the Kd represent? Now we've already seen the equation for Ka. That is where you have protein plus the ligand, Pl like that. And we said Ka is the concentration like this. Okay. Now we've learned from chemistry class that Ka right there, well, the Kd, or the dissociation constant, is going to be going from here to there. So now now it looks like this. Okay, that's our Kd. And so if we look at the rate constants, that'd be lowercase, like that. Okay. So what we have is an inverse relationship between Ka and Kd. We can say that the Ka equals 1 over the Kd. There's that inverse relationship there. And so if we take and do that same process that we just did for calculating the Ka, we can solve this equation for the Kd. And so what this Kd represents, okay, that is the dissociation constant at equilibrium. So that's looking at how well does this protein ligand, that complex, how easily does it release? Okay. And Kd, the dissociation constant, is in terms of molarity. Okay. Kd equals molarity, like that. Another thing that you need to be aware of is, I want to read this for you. So Kd, right here, is equivalent to the molar concentration of the ligand at which half of the available ligand binding sites are occupied. So let's take a look here. What does Kd equal? If we solve this equation, Kd equals 1 over Ka. And I just said that this point right here is 1 over Ka. So that point is also the Kd, okay, the dissociation constant. So when y equals 0.5, we extrapolate over on the graph, come down, this Kd right there. And that means, let me read it again, the Kd is equivalent to the molar concentration of the ligand at which half of the available binding sites are occupied. All right. And so what we can do here is take this equation right here, y equals this, right? And 1 over Ka equals Kd. So we can take this equation now and just plug in the Kd, like that. Okay. And this is just the easier way to do these types of calculations and do these studies with proteins that bind ligands in a reversible fashion. Okay. Now, how do you view the numbers when you're given a KD or a KA? What does this mean? Okay. So with a small KD, when the KD is small, that means that the protein and the ligand are binding very, very tightly. A small KD means that it's staying here, right? But a large KD means it's going to look like this. And so there's going to be a large dissociation constant, implying that the protein-ligand binding isn't very tight or very strong. Okay? So if we sum it up here, looking at these KDs and these KAs, we could say a smaller KD means a stronger binding affinity between the ligand and the protein. And also a small Ka means a strong binding as well. Okay? Sorry, I misspoke about that. So a large Ka means that it's bound very tightly. And then when we have a small KD, okay, that means we have less of this, which means we're going to have more of that, which means it's going to have a stronger binding. Okay? So small KD means strong binding, and a large Ka means strong binding. My apologies for the confusion. Okay. Now these equations right here are a general thing for most proteins. Okay, but let's come back to myoglobin. Now myoglobin is a protein that's binding oxygen, and oxygen, okay, is a gas. And so we need to take this equation and make some adjustments, okay? So we're going to just view it with oxygen for the ligand. Okay, we made that substitution right there. Now, measuring the concentration of oxygen in a solution can be rather difficult, okay? And so what we want to do here is, instead of looking at the concentration of oxygen, let's take a look at the partial pressures of oxygen. So you can measure partial pressures a whole lot easier because you're looking at the vapor above the solution. Okay? So we're looking at the partial pressures here. Now the KD, okay, is at 0.5, meaning at a certain concentration of oxygen, when half of the binding sites are occupied, that would be our KD. So what we can say is the KD is going to be the concentration of our oxygen, okay, at 0.5. That's just another way of saying what our KD is, right? The concentration of oxygen when we reach that point of half the binding sites are occupied. But that's concentration, so we need to convert that into, the partial pressures of that oxygen. And so when we do the partial pressure at 0.5, the textbook just takes this term here and draws it like this. Just the partial pressure of 50, meaning 50% of the binding sites are bound, okay, at that particular partial pressure. Okay, so the equation would look just like that. Okay. And with partial pressures, you would just go like this. You would get rid of the concentration brackets, like so. Okay. So for myoglobin, that is the new and improved looking equation. So let me just say it again just to make sure we're all on the same page. Capital P sub 50 right there. That is the KD. But it's just also, it's saying the same thing as what a KD would do. It just says that's the partial pressure, whatever it is on this x-axis. That's the partial pressure where 50% of the binding sites have been occupied with oxygen. Okay? Okay, so that's how we come to these equations. And so this is where I'll end this video.